All right, so we're looking at vectors, and we started talking about component vectors yesterday, and I want to expand what we know about component vectors to look at, kind of combine what we did the first day with vectors with what we're doing, what we did the last day with vectors. Okay? I want to combine the idea of our vector operations with component vectors. All right? And then we're also going to look at some beginning application of that here. All right, so the first vector operation we looked at on Tuesday was our vector addition. Okay, vector addition. And we used the head to tail method to add vectors geometrically. Right? But here we're going to look at the components, all right? So, if we have vector v, which is AB, and we have this other vector u that has the component CD, if we wanted to do u plus v, notice what we're going to do. We're going to add the horizontal components. We're going to add A and C, okay? And technically, since we did u plus v, the c would come first. All right? And then we're going to add the vertical components, b and d. So that's why we have d plus b. Okay? So you're just adding the components. It's pretty intuitive. I mean, if I had just given you a problem, you probably could have just would have guessed to try that anyways. Okay? What I want to show you, though, here is that, remember we said when we were looking at adding vectors geometrically, that it doesn't matter if you go like this and then go like this, or you go like this first and then go like that. We said vector addition is commutative. All right? Now, if you take any kind of a linear algebra or abstract algebra class in college, you're going to have to prove properties like that. I wanted to just show you this because it's really not as hard as it may seem. Okay? If I wanted to prove that vector addition was commutative, I would start with two generic vectors like this with variables, not specific numbers. And then I would try, hey, what's u plus v and what's v plus u? So I can see here, u plus v is c plus a, d plus b. V plus u is a plus c and b plus d. Okay? However, these right here are constants, right? And they're just real numbers. And we do know that the commutative property applies to real numbers, right? So I could then say, all right, well, I know since a and c are real numbers, that c plus a equals a plus c. And I know that since b and d are real numbers, that d plus b is b plus d. So therefore, I end up with the same thing I got when I did v plus u. And guess what? We've just proven that vector addition is commutative. And the reason why this is important is because when we're dealing with different mathematical constructs, so like we're used to dealing with real numbers, all right? But even when we worked with complex numbers, did all of the properties from real numbers automatically go over to complex numbers? Maybe, maybe not. Now we're dealing with a different construct. We're dealing with vectors. Or if we started dealing with matrices, can we multiply? Can we add? Can we find square roots? Can we do all of those same things we did with real numbers when we're talking about vectors? In some case, the answer is no. In some case, the answer is yes. Sometimes we have to redefine operations. For example, we have to define addition for vectors. You know? So here we're defining addition. Now that we have addition, do all the properties for addition back from real numbers apply to our vectors? Well, here we at least know the commutative property applies. All right, so you can see how this is something, if you get into some higher level math in college, and you have to take some of those things that deal more with the number theory, you'll have to consider these. But especially in this case here, it's not as hard as it may seem once you get the hang of it. Okay? All right, so there's your linear algebra for the day. Let's go ahead and actually use this stuff. Okay? So we have vector u, which is 4, -3, and vector v is 1, 6. So if I'm doing u plus v, what am I going to end up with? What, Vince? 5, 3. Okay. 4 plus 1 and -3 plus 6. That gives us 5 as our horizontal component and 3 for our vertical component. And if you think about it, this makes sense. If you visualized it, this makes sense. The first one, the first vector u goes over 4 and down 3. Okay? Vector v goes over 1 and up 6. Okay? There's vector v. So what's the net result? We ended up going over 4 and then over another 1. So there's our 5. We went down 3 but then up 6. So we ended up being 3 units above where we started. Okay? So there's our vector addition. The next thing we have is scalar multiplication. Okay? Yeah.
How is that different from yesterday or Tuesday?
Well, Tuesday we were just looking at, here's vector u, here's vector v. Oops. I'm bumping things. All right. Here's vector u, here's vector v. There's the resultant vector. We were just looking at it visually. We weren't really considering the components at that point. Now we actually have a numerical value related to that resultant vector. And what that would allow us to do actually is if we wanted to draw u plus v, we wouldn't have to draw out u and v. We could just say, hey, this is going to be our result. Okay? Now, scalar multiplication. When we looked at this geometrically, we said that scalar multiplication will change what? The magnitude, but the direction will stay the same. Okay? If v is 2, -6, then 4v is still going to go this direction. We're just going to have 2, 3, 4 of them. Okay? Same direction, just different magnitude. Okay? And that's going to be significant. But you'll notice here, how do we do scalar multiplication in the first place? We multiply each component by whatever the scalar is. Okay? So if we're doing c times the vector v, we're going to multiply the horizontal component a by c and the vertical component b by c. All right? So in this case here, I have the vector 2, -6, but now I need to multiply the 2 by a 4 and the -6 by a 4. So I end up with 8, -24. Okay?
But what if we had like -4? Wouldn't that then change the direction?
Yes, But if you're multiplying by -4, you're actually doing, you gotta kind of think of it as doing two different things. The negative is changing the direction, the 4 is changing the magnitude. I mean, I know it's kind of a matter of semantics or whatever there, but that's technically what's going on. Okay. Alright, now, I want to make a few connections here. Take a minute here. You guys know we used the Pythagorean theorem to find magnitudes of vectors, right? So we have vector v and we have 4v. So what I want you to do is take a moment here. I want you to find the magnitude of v and I want you to find the magnitude of 4v. Okay? So go ahead and use the formula we looked at on Tuesday and find your magnitudes here. It's horizontal, so you have 2 -6. That's going to make a right angle. It's perfectly horizontal. So what you can do, the magnitude is going to be the length of the side here.
What is it?
Plus 6 squared.
I think.
So 4 plus
Except for the 4, it's 40.
Okay. So you can use the Pythagorean theorem on your magnitude. Yeah.
When you take 4 out,
Think about this and what you missed. That's concepts involved or super typical. It's important to remember, so make sure you pay attention to notation, terms, formulas, and stuff.
We should take it on Monday or Wednesday during the central period.
I'm gonna give you the 65 minutes, just like you had. So, I mean, it'll carry over a little bit. When's your study hall?
6 period.
Okay.
Oh, do you have to play the actual balls in your bag too?
I've been playing in my lost
Okay. You want to play? And then we can cut out, but also you can do the.
I wouldn't do it
Is it
Monday
like free time?
I saw we have a quiz
You
on
get to
Monday.
when you get to
It's
everything,
not confident in my
It's on the fusion.
You get there.
Get you caught up on the new stuff and also make sure you're understanding the old stuff a little better.
And I'll see if I can put in by my study.
You like living in the door?
Yeah, that'd be good.
Get 24?
Yeah, and so you can
Oh, no.
Or-
Oh, I forgot to add, I put it there, but I didn't add it there. I'm just like,
Alrighty. There we go. No problem.
wait, so we started, what? So I taking the test for 7 periods. So, but you said we have an hour.
You have 65 minutes, so
After school.
they don't just carry over.
Oh, but I have an NHS. So what should I do? I think that's right now.
Either finish early or go to NHS 10 minutes late. Alright, what do we get for our magnitude for vector v?
4 root 10.
4 root 10, is that what you guys got?
I had 2 root 10.
You got 2 root 10?
Yeah.
It's the square root of what, guys?
40.
Square root of 40. So the square root of 4 comes out as a 2, and then you got the 10 left over. Alright? Alright. So you got 2 root 10. What did you get for the magnitude of this 8 negative 24? What was it?
25 roots 15.
Yeah, I don't understand.
No.
This is a radical 640. No, that's right.
The square root is 640, which 64 is, square root of 64 is 8, right? And then that leaves a 10 left over. Alright? So we've got 8 root 10.
Wait, how do you do that?
Well, you've got 8 and negative 24, right? So it's the square root of 8 squared is 64, 24 squared is 576, and you add those together, and you've got 640.
But why not negative 24?
Well,
It's just
when you square it,
Oh, yeah, gotcha.
yeah, when you square it, the negative becomes positive, so.
Oh, I think I got that, but just.
Otherwise, you'd end up with a negative number you're square rooting. So.
Yeah, I just don't.
Alright, now, what do you see?
It's 4 times the.
Alright. The magnitude of 4v ends up being 4 times the magnitude of v. So what do you think here? What, Hunter? It's just the magnitude of v times the constant. Okay? So check this out. We've got this vector v. We find the magnitude by using the Pythagorean theorem here. If I multiply that vector by a constant, I don't need to recalculate actually. I can just take the magnitude of v that I've already figured out and multiply it by the scalar. Okay? So for example, let's say I know that vector u has a magnitude of, say, 6. If I wanted to know what the magnitude of 5u is, what would I do? 5 times 6, yeah, it's 30. Alright? So that's pretty simple there, okay? Let me show you though where this can be really, really helpful. Let's say, before we get to the next thing here, let's say that we had a vector u, and u is the vector, let's go with negative 7 thirteenths, 24 thirteenths. Now I don't know about you, but using my formula and squaring 7 thirteenths and getting 49 169ths, and then adding that to 576 169ths, and then square rooting is going to be kind of a pain. But using this property right here, we actually can kind of do the opposite. We can kind of factor out a 1/13. What if I rewrote this as 1/13 times negative 7 24? Then you might recognize that as a Pythagorean triple, and the magnitude of negative 724 is equal to what? 724, what's the Pythagorean triple? 724? 25, okay? So guess what? If I now see this, I can just do 1/13 times 25, or 25/13. I don't have to mess with all the fractions because I'm using this property right here, okay? So this is one of the things that as you guys get more advanced in your mathematics, yes, this is a simple rule, but think about the ways that you can apply that rule to make your life easier dealing with problems, okay? So, now, there's an application here that I want us to see, and that is tying this together to a term that we had on Tuesday, and that term was the unit vector, okay? Vector v was 2, -6, alright? So, let's write that down here. V is 2, -6, and it's, well, let's be consistent in our notation. Pick one or the other. There we go. And we said the magnitude of V equaled 2√10. Okay? Now, question. I want to find a unit vector. If I want the direction of V, what can we do to a vector to keep the direction the same, but change the magnitude?
Multiply it.
Multiply it by something, right? That's what we just looked at. A scalar multiple keeps the same direction but changes the magnitude. The magnitude currently is 2√10. I want to change the magnitude to be what? If it's a unit vector. 1. Alright? So, think about what we just looked at up here. What could I multiply what could I multiply the magnitude of V by to make it equal to 1?
1 over 2 root 10.
1 over 2√10. 1 over the magnitude of V.
Um,
Okay? If C, well, you could even just solve this equation. C equals 1 over the magnitude of V. Alright? So, guess what? If I take V and I multiply it by 1 over the magnitude of V, okay, I've got 1 over 2√10 times that 2, -6. This vector here is going to have a magnitude equal to 1.
How'd you get the 2 -6?
That was the original V up here. We just were given that vector. Okay? So, looks like I need to give myself more room to work. So, now I multiply this. I would need to distribute this to both components. So the 2's will cancel out. I have 1 over √10, which is √10 over 10. The -6 and the 2 cancel out to a -3. So that's going to be a -3 over √10. So -3 √10 over 10. Okay? So this is what's cool about this. Now I have the same direction. I know I'm pointing the same direction as vector V was. My magnitude, though, equals 1. Okay? And the question here is, why in the world would we want to do this? What do you think? What could we do now? What if we wanted to go in that direction, but we wanted our magnitude to be 30 instead? What could I do?
And 30 on the unit vector.
Yeah, I can just, I know this has a magnitude of 1. I'm just going to do 30 times √10 over 10, -3 √10 over 10. So now I'm going the same direction, but now I have the magnitude I wanted. I wanted it to be 3, not 2 root 10. I'm sorry, I wanted it to be 30, not 2 root 10. So now I know that this vector would have to be 3 root 10 and negative 9 root 10. Okay? Does that make sense? Okay. All right, so a little application there that's really helpful. Okay, it gets us going the right direction at the right magnitude. Okay, so let's put a bit of this together. Okay, I've given you 2 vectors here. Take a minute. Let's see if we can put these ideas together. 2u minus 3v. All right, if this is vector u, 4, negative 3, and vector v is 1, 6, find 2u minus 3v. You didn't need to do this, I'm just prepping. You can do it one of 2 ways, either multiply by 3 and then subtract, or multiply by a negative 3 and then add. Just to make sure you don't use the negative twice. I'll tell you in a minute. But alright, what's 2u? What's 2u? 8, negative 6, right? And what's 3v? 318, okay? 318. So here's the deal. We've got 8 minus 3, which is 5, and negative 6 minus 18, which is a negative 24. So there's our vector, 2u minus 3v. It's 5, negative 24. And again, this is helpful because now we don't have to draw, here's 4, negative 3, and another 4, negative 3, and then minus 3v. So I've got to go the opposite direction of 1, 6, so it's going to be this way 3 times, okay? And I end up at 5, negative 24. I don't have to draw the whole thing. I now can do it mathematically and figure out, oh, I'm going to end up going 5 to the right and 24 down. Okay? Finally caught up. Alright? So, now that you have this vector, what's the magnitude? It'd be the square root of 25 plus 576. Yep. So we've got the square root of 601, right? What does that equal? 24.52. All right, so I put over here what the magnitude of u was. So what's the magnitude of 2u? 10. And I put here the magnitude of v. So what's the magnitude of 3v?
18.3.
Yeah, approximately 18.3. Alright, so if I'm trying to find the magnitude of 2u minus 3v, can I just do the magnitude of 2u minus the magnitude of 3v?
No.
No. Alright? I'd get a negative magnitude, which isn't possible anyways. Alright? So, be careful. That's a common misconception. People will just find, oh, I already know u and v, so I'll just do the same. They'll try to treat the magnitudes the way we treat the vectors up here to get the magnitude of the result, and that doesn't work. Okay? Alright, so last thing here. We've talked a lot about magnitude. The last thing I want to look at in the 5 minutes we've got here is our direction. Okay? This is a term that you need to make sure you know. When you're asked for the direction angle, or just the direction of a vector, what angle do you give? We've looked at bearings a couple of different ways. Alright? The direction angle for a vector, though, is the vector in standard position. Okay? It's the vector in standard position. So, you can see here, I have the vector AB. Here's my angle theta. Alright? If this is the vector AB, then the angle in standard position is the angle I'm looking for. Okay? Now, we already mentioned what this is related to, right? Because if this is A and this is B, how am I going to find theta?
Sine and cosine.
I think right there.
Tangent.
There we go. There's only one other choice. Tangent.
Oh my God.
Okay? Tangent of theta. Alright, tangent of theta is opposite over adjacent, B over A. We already said B over A equals what? The slope, right? The slope of that vector. Remember way back in chapter 1, we said that the slope of a line, if you equals the tangent of the angle that line makes with the x-axis. Alright? Well here, that's a direct application to right here. Okay? The slope is the same, rise over run, B over A. That's the tangent of the angle this makes in standard position. Okay? So, if I'm doing this, if I've got u, which is a vector 3, 3. Okay? Here's my vector u. I'm trying to find my angle theta here. So I'm going to have 3 here and 3 here. So I have tangent of theta equal to what? 1. What does theta equal? 45, okay? Now, technically here, guys, it equals 45 or 225. But, this is where you've got to look at your vector. Which one should it be, 45 or 225? 45, okay? If it were 225, that would be the vector -3, -3. Go in the opposite direction, alright? Now, we can see that here on this other one, on vector v, where we have to really think about that, okay? Vector v is 3, -4, okay? So here's our vector v. Now, if this is -4 and this is 3, here's our angle we're looking for. The tangent of theta, actually, I'm sorry, this is not the angle we're looking for, that's the reference angle. We're looking for theta. Okay? But, because that's a reference angle, we can still consider the tangent of theta equals what over what? -4 over 3. And if you use the inverse tangent, what do you get? Negative.
Negative 53.
Is it 53.13?
Yeah.
Okay. Is that the angle we're looking for?
No, you up 2 pi. You want like 3 something.
Yeah, add 360. Okay. Add 360. Okay, if we're in radians, we'd add 2 pi. Alright, so we add 360, and the angle we're actually looking for here then is 306.87 degrees. Okay. Now be careful, because tangent is negative in the fourth quadrant or the second quadrant. If it were negative 3i plus 4j, we would want the one over here in the second quadrant. Alright? So the equation would look the same, but you got to make sure you look at the situation and pick the right answer. Okay? Alright, that's it. That's it. Take some time to practice. We've got basic operations. Here we're finding unit vectors. Listen, please. Here we're finding unit vectors. Here we're doing the full process. Here's a vector. We want the vector in this direction, but we want it to have this magnitude. That's just like what we did with find the unit vector first, then make it have the magnitude you want. Okay? Alright, that'll be it for today. Have a great day, guys.